Okay, I think we'll get started. So today I'm going to talk about Fourier transforms. So this is definitely something that you won't find in the Gen Chem and General Physics books, regardless of what book that you have. And in fact, this topic is really not taught too much. If you were to have a college curriculum in chemistry or physics, you might see it a little bit. Even math, you might not see it too much. And the reason for that is to do a real rigorous mathematical treatment of it takes quite advanced mathematics. You have to get all the way up through complex analysis, have a good understanding of real analysis and calculus as well. So it just seems like it doesn't get put into the science curriculum, which is really a shame because the ideas that come from it give you so much intuition about how things work. So we're going to start that here in this very first Introduction to Physical Chemistry 1, and we'll try to talk about we'll build on these ideas as we move through our curriculum all the way up until we're able to do full-blown mathematically rigorous Fourier transform discussion higher up in our curriculum. But we want to pull some of the basic ideas. So after this, you certainly can't strut around to your friends thinking that you know Fourier transforms, but you'll start to know some of the ideas. And these ideas, again, really important and in chemistry, in instrumentation, in optics, everywhere. All right, so let's get started here, and let's just think about a simple cosine function. And the cosine function will oscillate with a characteristic frequency of, in this case, omega naught, and it'll have some amplitude, right? Now, we all know what a cosine looks like, and if we saw a picture of it, we'd say, oh, that's a cosine, and it has this frequency, right? So very easy to deal with in the time domain here. But what a Fourier transform does is it transforms to a different domain in which the x-axis is now frequency. And there'd be another way that you could talk about this function to somebody. You could say, I'm going to plot all the frequencies that are present, and in this particular case, there's only one. And so we have a spike here at omega naught. So if you look at this, you say, oh, my function in time has nothing but omega naught as a frequency. Therefore, it must be cosine or sine. We won't talk about how to tell the difference between sine and cosine, but you certainly can with the Fourier transform. And so the Fourier transform and its so-called inverse Fourier transform allow us to go back and forth to these two domains, the time domain and the frequency domain. And in this case, either one is equally convenient. Well, now let's look at the case of two cosines. And now you start to get a beating pattern, right? Or some kind of interference pattern. If they're close in frequency, you'll get a beat pattern. If they're farther apart, then you'll just get some kind of wild frequency. But you will notice, okay, this looks like this is probably a beat. Maybe this looks like there's two frequencies there. But if you Fourier transform it and say, let's just plot the frequencies that are present in this function, you get just two spikes. And so very, very clear. And the heights of these spikes are equal to the contribution of each type of cosine or sine. Well, now let's add a whole bunch of these. And then things get really messy in the time domain. And even just if adding several cosine waves, it's quickly hard to tell the difference between just complete noise and a lot of interference among a relatively small number of cosines. But if you do the Fourier transform, you can pull out each of these frequencies. Now, what these are called is the spectrum of the time domain function. So what we have in time, that's our time response or time behavior, and then what we have in the frequency space is called the spectrum. All right, well, let's look at something that has, in fact, an infinite number of cosines. What if we have a function that is not just a sum of cosines? then you're going to have all possible frequencies, but let's just look at one special function here, where we have e to the minus gamma t cosine omega naught t, and this is a damped exponential function. So say a molecule starts vibrating, but because it's in its environment, it'll lose the energy and then stop vibrating, thinking about this just as a harmonic oscillator. Well, it turns out that the Fourier transform of a decaying function like this is centered at omega naught. So it's centered at omega naught, and it has got cosines. It doesn't have just one cosine, but it has an infinite number that are decreasing as we move away from omega naught. And they're decreasing in the form of what's called a Lorentz function, or a Lorentzian function, but that's not too important to us. The idea, though, is that this is just a smooth function that dies off as you get further and further away from this carrier frequency, as it's called. Now, let's think of the limit here. If I make this gamma very, very small, then the decay is very long. It takes a long time to decay, and in the limit that I take that to 0, then I have just a cosine that goes on forever, and I have to have just a spike here. So if gamma gets very small, our decay is very slow in time, then our spectrum is very, very narrow. Conversely, if we decay very quickly, and I have only just a few oscillations of that cosine before the function's completely dead, then we need a lot of cosines to capture that behavior, and the function broadens out. And so the width of this is inversely proportional to gamma. So if gamma, is proportional to gamma. So if gamma is big, then the function decays quickly, and the width is big. If gamma is small, then the function decays slowly, and the width is narrow. And so the first key principle that you want to have, aside from just knowing this stuff, is that things that are fast in time are broad in spectrum, and things that are slow in time are narrow in spectrum. So let's just go through that again. Let me just get the decaying functions here. So if a function decays slowly, let's say number 2 here, then it's more peaked in spectrum, and if the function drops quickly, then it's broader in spectrum. So let's put all this together and talk about water, and let's first talk about water vapor and its vibrations. And so we've talked about this a couple of lectures ago, and we saw that there are 3 vibrations of water: a symmetric stretch, an anti-symmetric stretch, and a bend. And these are labeled nu1, nu2, and nu3. The symmetric stretch and the anti-symmetric stretch are almost equal in energy, and they're higher in energy, or higher in frequency, almost equal in frequency, and then the bend is lower in frequency. It's a lower frequency vibration. And so if we were to look at the Fourier transform of this, so if we were to look at the spectrum of the vibrations, we would see 2 spikes very close together at high values and 1 spike low. And these would be very narrow. I should probably put a little width to them. They won't vibrate forever, but they vibrate for a very, very long time as a gas. Well, now let's make water liquid. Now we have all sorts of intermolecular forces, but most pronounced for water is the hydrogen bond. This is a hydrogen bond. And the hydrogen bond gives a conduit for dumping energy into the next water and the next one and out into the system. So if this water molecule is vibrating, the hydrogen bond aspect allows it to dump that energy very quickly, and so the vibration will be damped very quickly. And so if we were to look at water's spectrum, we would see a very broad peak for the various vibrations. And in fact, we wouldn't even be able to distinguish the antisymmetric from the symmetric stretch for water because they would be too broad. All right, let's just finish up with a few prototypical Fourier transforms. If we have a decaying exponential, so e to the minus gamma absolute value of t, then we get a Lorentzian function. And this looks like gamma over omega squared plus gamma squared. There might be a 2 up there. I can't remember for sure here. Now, if we have a Gaussian, then we have a this is a unique one. This is also a Gaussian. I'm going to use a different variable here. Let's call it beta omega squared. All right. So if alpha is big, then this will decay quickly, and this will be broad. So the Gaussian is unique, or the normal distribution, or the bell curve is unique, that the Fourier transform of a bell curve is a bell curve, or a Fourier transform of a Gaussian is a Gaussian, but the widths are inverse to one another. Let me see, did I make a mistake over here? So if this is big, then this is big. Okay. Looks like I'm fine. Then let's look at a square. This is something that doesn't come up so much with molecules, but it comes up in instrumentation. So if we're sampling data, we can't sample it forever. So we stop sampling with a certain window. And when we have this, the fact that we have these sharp points gives us frequencies that are very big on either side, and it also gives this ringing effect. And this is called a sinc function. And so in shorthand, it's sinc omega, but what that really is sine omega over omega. So a window function gives rise to a sinc function. And then a triangle gives rise to, turns out, a sinc squared. Function. And there's constants in there that we have. But again, if we have a narrow window, so if these are squished, or a narrow triangle, then we're fast in time, then this will be broadened out and spread out. If we have a big window, or a slowly decreasing triangle, then these will get squeezed in, and we will get a sharper spectrum there. Okay. All right, so this is our first taste of Fourier transforms. Such an important concept throughout all of physics, and it goes very deep, just right to the heart of quantum mechanics, practical applications in instrumentation, and the heart of any kind of spectroscopy where we can use light to pull information out of matter and materials. So start to just internalize these ideas. You don't have to feel like you have to know any of the math, but start to build an intuition about this. And so let's summarize. A function is broken down into its various oscillating components, sine and cosine. If something decays fast in time, it's broad in spectra. And we can use the spectra to easily identify from a mess of vibrations. And so water with 3 here was an example, but we could have benzene or carbon tetrachloride or whatever, and we might get a spectra that's quite complicated and would look extremely complicated in the time domain, but it sorts itself out nicely in the spectrum. All right, so that's Fourier transform.